So yes, today I'm going to be talking about the work that I've been doing, developing capabilities with uncrewed aircraft systems for measuring methane from dairy farms. And so I will first start with a motivation. So why are we interested in measuring methane? So as we all know, methane is a powerful greenhouse gas. And in the state of California alone, it's estimated that dairy farms can produce up to 50% of the emissions produced in the state. However, the methane emissions are still very uncertain. So to lower the uncertainty, we need higher fidelity observations of winds, turbulence, and air composition within the planetary boundary layer. So I've been working to explore how we can use aero-robotic systems to complement existing remote sensing capabilities, whether it be satellite-based or aircraft-based. Okay, so in my work, what we've done is, so this has been a collaborative project that actually happening at UC Riverside. So this is with Don Collins and Francesca Hopkins. And so Don Collins and a graduate student of his developed or constructed an Aircore. Some of you might be familiar with the Aircore, some of you might not. So I'll explain what an Aircore is. So an Aircore is essentially a coiled tubing, and so it's about 50 meters long. And so as we show in the picture here, so this is a coil that is hanging about 5 meters below the aircraft. And so what we do is we do these vertical flight operations that begin at the surface and extend all the way up to 120 meters. We can go higher, but going higher would require requesting permission here in the USA. And what the air coil does is that it retrieves an air sample as it ascends and it descends. And so we conduct these operations downwind of a source. Here below is a picture of the Aircore. So once we fly and come back and retrieve the air sample, then we use a CRDS analyzer to determine what the air composition is. And so the neat thing compared to about this technique compared to other methods is that we are able to retain the structure of concentrations, as I will show you. We did an experiment in the Central Valley where we deployed the aircraft-based Aircore system downwind of a dairy farm. And so to the left is a picture of the Aircore flying. So it's just taking off and it's ascending up to 120 meters. And it's operating, if you can see in the middle here, my pointer. So it's operating downwind of the of a dairy farm. And in this particular case, the dairy farm was fairly isolated, so we considered it to be a good case for exploring how well we can measure emissions from a dairy farm using an aircraft-based Aircore or a drone-based Aircore. And so for you to get a picture of the facility, so the facility is about 800 meters wide and 945 meters long. And so here, this graph, what I'm showing you on these 3 panels are how the wind speed, the wind direction, and methane concentration, or ppm, is changing with altitude. So let's see. So we descended, we're able to collect. So the blue is the measurement that was collected during the ascent, and then the red is what we collected during the descent. Very, very interesting thing that happened during this flight operation, as you can see, is that while we are ascending, the winds are coming in from the south, and as we get to the top, we see a shift in the winds. They become unstable, and then they shift to the north. And so we can see by looking at the measurements that we get from the Aircore, we can see that ascending, we captured a 2-peak feature, which we think is the plume that's coming from the source. And then coming down, we still saw some emissions, but were much less significant. So then we've essentially done a number of flights downwind of dairy farm operations. And so then The measurements that we are collecting from the drone, so these be the wind measurements and the air composition measurements, have been combined with a dispersion model. And so to the left, I'm showing you a footprint map that we were able to obtain with the dispersion model. So we are essentially using the wind measurements as inputs to the dispersion model to determine the footprint of the emission source. And you can see that the dairy farm that of interest is actually well within the footprint. But to validate that this scheme is really working, more recently we've conducted tracer gas experiments at UC Riverside. So these are experiments where we ourselves generate a source. Of course, it's at a much smaller scale, but it's a good thing to do to validate how well our dispersion model works. And so what we did was we released, in this case, ethane into the atmosphere. And then downwind of the source, we had receptors at different distances and different heights. And we had sonic anemometers to measure the local wind conditions. And so just to kind of show you some of the results that we are getting from our dispersion modeling results is that our dispersion model is actually performing fairly well, predicting emissions from our source. So I will focus on the plot to the right. So this is what you see on the horizontal axis are the different receptors, and then on the vertical axis are the concentrations. In this case, we released ethane instead of methane, and the red shows us the measured, and the blue shows us the predicted. So that gives us we have high confidence that our dispersion model is working fairly well. So the advantage of this is that by using the aircraft-based Aircore system, we can take vertical profiles downwind of the dairy farm, so we don't even have to go to the dairy farm, and we combine that with dispersion models, and we can estimate what the actual emissions are. Here to the left, I'm just showing you the comparison of emissions. So we're comparing both to a bottom-up estimate, and so this bottom-up estimate was generated by Alison Marklin, who was also here at UC Riverside working with the Hopkins lab. And then an estimate that was generated at this dairy farm using a mass balance approach. And to the right is the dispersion model results. And so you can see that overall there's an overlap between the uncertainties when we look at the bottom-up estimates and then the dispersion model. The agreement is less when we compare to the mass balance, but overall from these experiments, we're able to conclude that the aero-robotic systems and Aircore technology can provide us this new capability to profile just downwind of an emission source. And then these profiles that we are obtaining can be combined with dispersion model to generate emission estimates that are of lower uncertainty. And if we have emission estimates with lower uncertainties, then we can do better generating mitigation strategies. And then just very briefly as to the future work / ongoing work is we are now spending some time modifying the Aircore, looking at, oh, this is a video, it's not showing, but basically we've generated a new Aircore that has multiple inlets and we can fly it downwind of dairy lagoons. And so the objective now is to not only try and get facility scale emissions, but also sub-facility scale emissions. We're also combining this technique with mobile lab measurements as well as bag samplers that can take integrated measurements and just to try and get a better picture. Moreover, we're extending some of these techniques to also obtain measurements in oil and gas field. So this is part of the summation project. And so what we do, we basically leverage carbon mappers. Maybe a majority of you might already be familiar with carbon mapper to look at some sites where infrastructure might be leaking. Then we deploy our, these are the air samplers. We measure concentrations and then we run our dispersion model. So in the next steps, we're going to be thinking about how do we incorporate Aircore technology to get a vertical profile and really understand what the emissions are that are coming from these facilities. But overall, so we just wanted to show you, by doing this, we can actually get emission estimates, basically a time history of emission estimates, and be able to understand how emissions are changing with time due to wind conditions and other environmental parameters. But yeah, with that, this is basically what I wanted to showcase. And so I just want to end by thanking my collaborators, UCR collaborators, so Dr. Don Collins, Dr. Kula Venkatram, and Dr. Francesca Hopkins, as well as the graduate research assistants, Yifan Su, Yifan Ding, Valerie Carranza, Isis Frosto Vicencio, and Rangarajan Thiruvenkatachari, as well as the funding and research support.
So yeah, today I want to talk about what we've been working on with Daniel Varon, my supervisor here at the Atmospheric Chemistry Group. Basically assessing the potential of current geostationary instruments to detect, locate, and quantify methane emissions events, extreme methane emission events. So I want to start off with this image that you've probably seen in previous talks. This is the current fleet of satellite instruments that are able to detect methane from space. And all of these have one point in common, that is that they are all in what is called low Earth orbit. Just quickly going to move the... Okay, good now. They are all in low Earth orbit. That means that they are fairly close to Earth, and they are orbiting over localized regions. I'm going to show a visual of this. It's always easier than to explain it with words. This is Sentinel-2, and you can see it's in a polar orbit and shifting its orbit successively to scan different regions. And this has a major implication in that the time it takes for the satellite to take two successive images of the same location, that is called the revisit time. So the time it takes for the satellite to come back and take a second image of a given place is measured in days at the minimum, and in some cases in weeks. And that's a big problem, of course, because the coverage of these satellites to detect these emissions is very much limited by this revisit time. And maybe Colette will also speak about it later on, but this also difficults our ability to kind of quantify the intermittency of these events. When do they start? When do they end? How long do they last? Do they happen more in the morning or in the afternoon? And this is something that's really hard to kind of know with only a single snapshot every few days or few weeks. And so wouldn't it be cool if we had an instrument that was capable of monitoring large areas continuously? And wouldn't it be cool as well if that satellite was already there and we didn't have to wait 10 years for the mission to launch? And so that's what I'm going to try to motivate here. We're going to talk about a different kind of satellite, geostationary satellites. In this case, I'm going to focus on GOES. So GOES is the constellation of geostationary operational instrumental satellites operated by NOAA. It's not a super recent mission. It was launched in 1980 to monitor land and atmosphere across the American continent. But importantly, in 2016, the new generation of GOES satellites, replacing the old ones, added two shortwave infrared bands that are going to be really important for us. In fact, they are similar to the shortwave infrared bands used in Sentinel-2, for some of you that know that Sentinel-2 can detect methane for the last couple of years. And in fact, these two bands kind of overlap to the methane absorption features in the shortwave infrared, so between 1.6 and 2.4 micrometers. You can see this, there's a small one on the left and a bigger one on the right that overlap with this methane absorption region of methane. And so that's what we're going to exploit to try and basically adapt the multi-band, multi-pass approach that was used for Sentinel-2 to the GOES instrument. And the important thing, as I mentioned, for this satellite is that it's no longer in low Earth orbit. It's much further away from Earth, and that allows it to basically sync its orbit to the Earth's rotation. So basically, the satellite is always looking at the same region of the world. So that's what we get, 5 to 10 minute revisit times. Remember, we were talking about multiple days or weeks for low Earth orbit. And 5 to 10 minutes is the time it takes for the satellite to take an image of on a given point in time. The satellite is a bit far away, so of course we're not going to get this super great 20-meter resolution like Sentinel-2 or even JHG-SAT. It's a 1-2 kilometer pixel resolution, but we're going to show that this can still provide some useful information on these huge events. So, okay, the first thing we need to do if we want to build a retrieval and test it out is, of course, somewhere where we know methane is present. And the good news is there's a lot of satellites that are pretty good at doing that. In this case, we're going to use Sentinel-5P, which embarks the TROPOMI instrument that has a dedicated methane product. And in this case, we chose the a Mexico detection from 2019, pretty big one. And we basically implemented the multi-band, multi-pass approach, adapting it to the GOES instrument. And so after a few months of work, this is what we get. You can see here the 5-minute by 5-minute evolution of this plume. We can clearly see when it starts, how it develops, and when it ends, when the plume detaches from the source. We can also kind of know where the emission started. So in this case, it was a block station or block valve that from a natural gas pipeline transporting natural gas from the Permian Basin into Mexico. And so these block stations are used to separate segments of pipeline for maintenance and so on. And so that's very cool. We have a detection. Of course, the next step is to quantify this detection, right? And so to do that, what we're going to do is we're going to first select the pixels that contain the plume at each time step. Once we get this spatial information, we can convert concentrations into total methane present in the growing mask. And we can then plot this quantity in function of time. So you can see here in red, this is the evolution of the methane contained in the mask. And you can see there was a pretty big emission, more than 1,000 tons of methane emitted over the 3-hour duration. We can also have some fun and try to kind of compute the time-dependent source rates of the emission. In this case, it's the blue line I'm showing here. You can see the emission kind of ramped up in the first 30 minutes. And then probably as the pressure in the pipeline started to drop because of the methane exiting, this source rate started to drop as the emission ended. So GOES, as I mentioned, is looking at the American continent. And looking at this map, we would like to see other regions of the world, right? And the good news is GOES is not the only geostationary instrument out there. Himawari, for example, which was launched in 2014, even more back in the past, is a Japanese geostationary instrument that's looking over the Asian continent. And critically, it also has these two shortwave infrared bands. And so basically, the methodology that we implemented for GOES can be applied to Himawari as well. And now Europe and Africa is missing. So of course, there's another one. In 2023, MTG was launched by the Meteosat, and also has these two shortwave infrared bands. So again, the technique can be applied there too. And so you can see this, that with these 3 satellites, we already get a pretty significant coverage of the world. So as I mentioned, and if you couldn't tell by my French accent, I worked at a French company called Kairos for a year before joining the group. And over there, this detection that I'm showing here was kind of a rock star. That is because it's quite pretty uncommon to have a double detection on the same day very close by. You can see there's 2 separate hotspots separated by a few tens of kilometers, pretty strong as well. And so this was basically the detection that we showed in the demos and so on. And so when we got our retrievals to work, I kind of wanted to have a look if we could get some more information with GOES. And sure enough, when you run the retrievals, you can see that it was a simultaneous release, plus minus 5 minutes, over, again, a natural gas pipeline. So between the 2 crosses, there is a natural gas pipeline in the middle. And again, right beneath it, the same kind of infrastructure, the block station that I was mentioning before, for 45 minutes. And in fact, if you were to come back to only got the information from TROPOMI, you would probably say, okay, it's somewhere in Illinois. I'm going to have a look if there's any compressor station underneath or any pipeline. But in fact, with GOES, when you run the retrievals, you find out that it was not even in the same state. It happened in Indiana, more than 60 kilometers away. And what you're seeing with Sentinel-5 is actually the cloud of methane that has kind of been transported downwind into Illinois. So that's what GOES can be really good at. Okay, that's the last detection I'm showing, I promise. This is an emission over the Permian Basin, a bit of a smaller one, 100 tons per hour, still significant. But here, what I want to emphasize is that the emission is very short. It only lasts about 20 minutes. And so if you come back again to the low Earth orbit paradigm with 5 days revisit or something like this, the probability of a low Earth orbit overpassing the region on this 20-minute window, you can see that it's pretty unlikely, and we're probably going to miss it. And so that's what GOES can do, is it can monitor these short in time duration large events continuously. So we have a preprint out. I want to thank Daniel Varon, of course, Nick Balassos, ITCR, who've helped a ton in making this project advanced in the past few months, and Jack as well, and Francois. But yeah, if you want any more technical details, I'm sure you'll find it interesting, hopefully. And if you have any feedback, also, we'll be more than happy to receive it. And in the meantime, I'll be happy to answer any questions that you might have. Thank you.
Yeah, so my name is Colette Schissel. I'm a Ph.D. candidate at the University of Texas at Austin. I work with Dr. David Allen. And today I'll be presenting on understanding temporal extrapolation uncertainty in measurement-informed methane emission inventories. And I'll be looking at the Barnett Shale as a case study. So just to provide a little bit of background on methane measurement and measurement uncertainty in the context of constructing oil and gas emission inventories. As I'm sure most of you know, measurement technologies span a wide spatiotemporal range with technologies such as satellites or aircraft mass balance flights, which provide information on a large region or area. And then we have technologies all the way down to individual source sensors, which provide measurements at the source level. And regulatory agencies and voluntary initiatives are beginning to incorporate measurements into developing annual inventories. And these different measurement technologies are best suited for detecting different types of emission sources. And so using kind of a robust constellation of measurement technologies can give a really interesting picture of a region. However, using different technologies often gives you different answers or different numbers. And it's very difficult to arrive at a set number for an emission inventory. Reconciliation is difficult for a number of reasons, but importantly, we have to understand that both of these estimation approaches and techniques have a significant amount of uncertainty, and quantifying that uncertainty is crucial for making meaningful comparisons. So methane emission uncertainty, I think, is best broken down into three parts. The first is measurement uncertainty. And so this is the uncertainty that's associated with the primary mode of measurement. So for example, in a LiDAR technology that emits a pulse of light and measures the backscattered pulse, the primary uncertainty here would be associated with that actual kind of detection. And in relation to the other forms of uncertainty, typically this is actually quite small. The second form of uncertainty is emission rate uncertainty. So that refers to the uncertainty in the calculation process of converting this primary measurement to an emission rate estimation. This process typically involves the use of meteorological data and dispersion modeling. And so this step can introduce significant uncertainty depending on the quality of that data and the rigor of that model. And then the final stage of uncertainty, which I'll be touching on today, is extrapolation uncertainty. And this is the uncertainty associated with taking a collection of measurements and extrapolating them to a larger region or a larger scale of time and space. And so there are two forms of this that I'll break it down to. I'll first talk about spatial extrapolation. And so spatial extrapolation refers to taking measurements of a sample population and extrapolating that to a larger asset or region. And then finally, the focus of the work today is on temporal extrapolation. So temporal extrapolation is taking a collection of short duration measurements and then scaling these up to an annual inventory. So taking a couple of days worth of measurements or a couple of hourly measurements over the course of a year, and assuming that that's representative of an entire annual inventory. So I'll be looking at how to quantify this temporal extrapolation uncertainty and identifying some of the factors that influence this uncertainty using the Barnett Shale as a case study. So the Barnett Shale is a natural gas production region in north central Texas. It was selected for this case study because it's a pretty well-studied region with lots of available measurement data. And emissions from this region are characterized by a highly skewed distribution where the top 1% of emission events contribute to about half of total emissions. So the analysis for this work was kind of broken down into two parts. The first was to simulate the emissions in the Barnett Shale. So to accomplish this, I simulated 50 sites representative of the Barnett Shale based on production distributions and site configuration distributions. And I simulated this using a methane emission estimation tool, also known as MEET. And so MEET computes a temporally and spatially resolved emission time series. And the MEET output was then processed to add on these distinct high emission events. And they ranged in duration from 6 months to 1 hour. And the number of events changed such that we could maintain a constant high emission event rate of 1% of the time. And so these figures just show a few representative time series that were used. So on the left here, we have, at the top left here, we have the 50 site aggregate with a 1 day average emission events. And then just below that, we have a single site. So the 50 site aggregate was essentially an overlay of 50 sites altogether, if you could kind of imagine taking a snapshot measurement that covers that entire region. And then on the right here, we have a time series with having that 1 month average, and similarly a single site versus the aggregate. So 6,000 time series were generated, 1,000 for each defined event duration. And with each iteration, different start times were selected for these emission events, as well as emission rates based on observed emissions. So the next step was to simulate these measurements. So essentially a 1 minute snapshot was selected at each defined interval, ranging from 1 measurement per year to weekly measurements per year. And in this step, it was assumed that there was kind of a perfect measurement. So there was no emission rate uncertainty. There was no primary measurement uncertainty. It was just focusing on how well these different snapshot measurements captured the temporal variability. And so the number of measurements collected per year were averaged together and then compared to the true emissions emitted per year to compute an error. And so what we found is that temporal extrapolation uncertainty can be very significant. This table shows the average absolute error as a function of the event duration and sampling frequency across the 1,000 simulations. And so individual instances as well exhibited higher error and variability. And so as we might expect, increasing sampling frequency decreases the error, and it also decreases the variability of that error between simulations. But as we looked at general trends, we noticed kind of a key parameter that fell out of this analysis. So we defined the duration ratio as the average duration of these significant intermittent events divided by the time between sampling. And we noticed that if the duration ratio is greater than or equal to 1, meaning that the minimum time between sampling was just as long as the event itself, that if it was equal to 1 or exceeded that there was a steep decline in error. So for example, if we look at the monthly sampling, if we have kind of short duration intermittent events, the average error kind of hovered around 20%. But if these intermittent events persisted for longer than a month, longer than the time between sampling, it dropped off to about an average error of 4%. So just to kind of round this out with some main takeaways, the purpose of this paper was to understand the significance of temporal extrapolation uncertainty and the factors that influence this uncertainty in the greater context of understanding what kind of variables we should consider when comparing and assessing methane measurements. The main takeaways that I want to leave you with is that understanding uncertainty is really important for developing meaningful understandings of these methane measurements and comparing these. And of these different types of uncertainties, extrapolation uncertainty is a potentially significant source, and it depends on both the frequency of the sampling as well as the underlying characteristics of the emissions that you're trying to capture. And because of this dependence on the temporal behavior of the emissions themselves, it's going to be important to understand the time varying behavior of emissions and be able to understand what these durations look like, especially when designing measurement campaigns as regions with near continuous emissions might require a very different sampling strategy with regions with highly intermittent, highly short duration emissions. So that's all I have for today. Thank you for listening. And if anyone has any questions, I'm happy to answer.
Great. Thank you, Colette. That was absolutely excellent. And this gets to, I think,